Do we expect it to deviate more? All right, 3. Okay, other questions?
Can we go over number 4 that I was talking about, which favors product formation?
Number 4, okay, let's take a look at that. Are we going to completely ignore activities? No, we aren't in this class. We're actually going to factor those in one of our labs. And so we're going to compare a calculation we do by hand versus with stoichiometric concentrations versus one with activities. All right, let's see. It's the wrong class. Well, at least the e-text loaded. This morning it wouldn't load. Now the sample test is not loading. Let me try it. Sad thing is this is a pretty new computer. This computer is less than a year old. But they loaded so much stuff on for other departments. You know, they should just keep it to the chemistry stuff.
You want to borrow my...
Just read out the question, that'll be faster.
Let's see, so it's a CaCO3 solid, and it's the double arrows to CaO plus CO2 gas. So CaO is solid as well.
Okay.
Okay.
What's the question asking?
It says which favors product formation, and the options are adding more CaCO3, removing CO2, both, or not, or neither.
Well, the thing is, what's going to favor shifting it one direction or the other? And we want to shift it to the right. So normally we would think removing product or adding reactant, but the situation is it's a little bit more complicated than that because the concentration is going to impact it. The concentration makes a big difference because if let's say you have 5 gallons of 6 molar hydrochloric acid versus 6 gallons of 6 molar hydrochloric acid. You know, 5 gallons versus 6 gallons, you think, oh, 6 gallons is more hydrochloric acid, therefore it's going to be more reactive. Is it going to be more reactive? No. Really? Not really. You know, you'll get more reaction out of it, but it's not going to be more reactive because it's the same concentration. Versus if you had 5 gallons of 6 molar versus 1 gallon of 18 molar, you know, you'd say the 1 gallon of 18 molar should be much more reactive because of its concentration. And so with pure solids and pure liquids, by adding more solid or removing solid, it doesn't change the concentration. It's still pure. And so when I look at the solids, those are automatically, I can't change that because it's 100% pure. How can I make something 100% pure even more pure? You can't. And I can't even make it less pure. I can just remove some of it. That's it. Well, if I remove some, it's still going to have the same reactivity. It's just going to not react as much. And so the only thing here you can do to change it is to add or remove CO2. You know, if we add CO2, then it should shift it to the left. If we remove CO2, it should shift to the right. That is, if, you know, adding or removing CO2 will change the concentration or the pressure. And so we have to remove the CO2 from there. Uh-huh.
So adding calcium carbonate would have no effect?
No effect. You just need a little bit, and that's all you need. Yeah.
So I remember you saying something about solids that concentrations?
No. Solids don't have infinite. Solids have a concentration that does not change, a constant concentration. Right. It's like water. You know, if you take 1,000 milliliters, a liter of water weighs 1,000 grams. And so if I have a liter of water, that's 1,000 grams of water, that comes out to 55.5 moles. And so the molarity of pure water is 55.5 molar. It never change. It doesn't change. And so if I had 2 liters, would the molarity change? No. And so the reactivity is going to stay the same as far as, or the activity, I should say. Activity stays the same. The activity is constant. That's why it gets an activity of 1, but it's not infinite concentration or anything like that. It's just got an activity of 1. That is, it doesn't change. It's not going to impact everything, so we just factor it in rather than actually calculating it in there. Uh-huh.
So you know, just for number 4, you gave the example of if you have a 5 gallon of 5 molar HCl and a 6 gallon of 5 molar. So then for number 7, since it's saying that the H plus concentration is 3 molar and the iron 3 plus concentration is 18 molar, then the reaction would shift, like if, because the iron 3 plus is on the product side, would it shift to the product side?
Iron 3 plus is on the reactant side,
On the product side.
on the product side, and
And the H plus is on the reactant side.
what was the reaction?
FeOH3 plus 3 hydrogen.
Okay, 3H plus.
Yeah, 3H plus yields iron 3 plus 3 water.
This reaction here?
The arrows are the ones that you
Like this?
can, yeah.
Yeah. All reactions can be shown with a double arrow like that. And so what was changed?
It says asking if the hydrogen concentration is 3 molar and the iron 3 plus concentration is 18 molar, then which direction would the reaction shift?
Compared to what?
That's just,
There's a K value of 9.1 times 10
Oh, okay. Compared to equilibrium, so it's
Yeah.
it's a Le Chalet's value. And so the system's at equilibrium. This is one thing is, it's hard to tell, you know. And the K value is, what was it again?
9.1 times 10 to the 3rd.
9.1 times 10 to the 3rd means that that's the proper ratio of products to reactants. And the H plus concentration was what?
3.1.
3.0?
Oh,
Fe3 plus?
18.
And so, looks like it should shift this way, but we don't know because of it's nonlinear. Because of this 3, coefficient of 3 will make it a Q. And so all we do is we calculate Q. Q is our current ratio, and C doesn't match K. You know, K is what it's supposed to be, the product to reactant ratio. And so if we look at Q, Q is just going to be the iron 3 plus that's given over the H plus concentration Q. And so it's going to be 18 over 3Q, which is 9. Which is equal to 2. And so 18 divided by 9 is 2. When we compare Q, 2 is too small. It has to be 9,100. And so it's got to shift to the right. You know, even though this seems high as is, it's got to shift to the right because yeah. So it's going to shift right. Now that's assuming we have enough. You know, because we have enough because this is pure solid. And so we have to have enough pure solid so that it can shift right. But whenever we have a solid or liquid, we're going to assume that there is enough to maintain equilibrium. So therefore, I'm just going to write a line through solids and liquids. That line doesn't mean zero. That line means we have enough. Sometimes we actually have to calculate the amount that's reacted. We can calculate the amount that's reacted, how much additional iron-free hydroxide has to react in this, depending on what the final equilibrium ratio is going to be. So the molarity of this has to go way down. It's way too much to sustain at equilibrium. So let me try. Maybe it's a problem with. Yeah, maybe there was a problem with edge. Edge was not letting me open it.
So when Q is smaller, products are favored?
Yeah, because the ratio is too small. When Q is too small, products are going to be favored. And so this is just a Q versus K. You know, is our current ratio the same as our equilibrium, or is it too small or too big? If it's too big, then we have too much product. If it's too small, we have too little product. So we get to change it. All right, any other questions?
Yeah, for number 2, I wasn't sure if it was a trick question or not. This just seemed kind of easy. Like, since it's KP so high, does it just favor products? Or?
The equilibrium, yeah, 2 hydrogen. KP is enormous, so it favors product.
Okay, I just wanted to make sure.
Yeah, that's seems like it'd be a trick question, but it just favors product.
Okay.
That's a huge ratio. All right, other questions? Uh-huh.
Number 16.
Number 16, how many people have figured it out? Number 16. You got it? Did you complete it? Double check it?
Yeah,
It came out okay?
but I kind of messed up too at the same time, so I'm not really
Oh,
too
okay.
confident with my answer.
Not confident?
Yeah.
Well, as long as the equilibrium, you know, if you double check it and it comes out to KC, you're okay. I see, you know, number 16, you see a lot of mistakes with number 16. We'll just talk about some mistakes. You want me to, obviously it's getting down to the wire, so.
You just go ahead and go.
This is a practice test, so you're supposed to try to treat it as real. You know, because there are homework problems like this that you could do, you know, with the solutions manual. In fact, this is it's kind of like a homework problem. KC is 1.09 times 10 to the 5. One thing I look at first is KC, it's big. And just like that, KP was huge for water formation. And we're starting off with 0.100 of everything.
Would you say like anything over 10 KC is resettable?
Anything is resettable. You know, it's just, is it worth resetting? That's it. This one is worth resetting. Well, one thing is we don't know, does it shift to the right or does it shift to the left? You know, you don't know by looking at this necessarily. Well, actually, it's because, you know, this is the two, it's gonna be fourth order, third order on the top, fourth order on the bottom, so it's kind of tricky. You can't just say KCQ is 1. Doesn't quite cancel out. And so one thing is I don't know which way this shifts. Is it minus, minus, plus, plus? I don't usually bother. You know why? No, I just one, KC's big, so I just reset it. Why bother doing Q? It's just, for me, unless that's the purpose of the question, the purpose of the question is to answer which direction it shifts. Like this one, number 7, I would bother doing it. But for number 16, I think it's a waste of time. I wouldn't bother doing Q. I don't care which direction it shifts. It could go to the right or it could go to the left. I don't care because there's too many binomials to deal with. So automatically, I would have reset this one. Which side would you reset it to?
Product.
To the products. Yeah. It doesn't even even if KC is 11, I probably would have reset it because it's just too many. But to do this properly, you would calculate Q, and then compare it to K. Probably shifts to the right. But to reset this, what would it reset to? Or, every semester there are people who are really uncomfortable with resetting it. You don't have to reset. We don't have to reset this. If you just like, are there any people who, oh, well, is everybody comfortable or not so comfortable with resetting?
Kind of have to
Yeah.
Yes, you have to be, but, you could still make some progress without resetting. So normally what we do without resetting is we just hit Q. We figure out what Q is. So that's going to be 0.1 squared, 0.1 cubed. 0.1 cubed divided by 0.1 to the 4th gives us 0.1 to the minus 1, which is 0.01. And so Q is 0.01. It's way too small, so it's going to go to the right. And so the change here is minus 2x plus 2x plus x. And then at equilibrium, I'm going to get 0.100 minus 2x, 0.100 minus 2x, 0.100 plus 2x, 0.100 plus x. And then solve it for KC. On the test, you should write, especially if you're going for partial credit, you should write as much as you can. If you're really sure you got the answer correct, then you can skip some stuff. Still get full credit for the problem. And so I'm going to write this here. So the top is going to be 0.100 plus 2x times 0.100 plus x plus 2x is squared divided by bottom 0.100 minus 2x squared, which would be 4. Can you use a simplifying assumption here? No, you can't use a simplifying assumption in a problem like this because x would completely drop out and there's no x to solve for. So that's an error I see. When I gave this test last time, maybe about 5 people made that error. They tried to do the simplifying assumption here. X dropped out and they just calculated the ratio and used that as the answer. Does that make sense? So about 5 people did this. They used the simplifying assumption and then they calculated this and used that as x. They said x equals that. Well, that's wrong. X disappeared. You can't do that. Some people did the successive approximations at this point and started guessing x values. And that's okay. You might get lucky and get it. it depends on how much time. It's not a matter of luck, it's just a matter of persistence, If you persist at this, you'll get it. It's just if you can get it within the time frame. I'll tell you, nobody who did successive approximations on this equation got it. Nobody who did that was able to get it. And so the successive approximations would fail at this point, and then some people reset it, but I look for things when I reset it. Some people reset and don't pay any attention to coefficients and don't pay any attention to limiting reagent when they reset it. And so a lot of mistakes with the reset here. And so and this one was easy though. This one, is there a limiting reagent? No, this is what we call stoichiometric. It's the right amounts of both. They're in stoichiometric ratios, so this goes to 0, this goes to 0. And so this is minus 2x, 2x is 0.100. If 2x is 0.100, this is plus 2x, this is going to be 0.200, and this is plus x, so this is 0.150. And so a lot of people put 0.200 and 0.200, which is wrong. They didn't get the coefficients in there. They didn't get the y, which I call a y when I reset.
So is the higher coefficient always going to be the limiting reagent?
No, the coefficient makes no difference at all. It's what you're given, the initial. Both of these have the same coefficient, so both are the limiting reagent, but what if I did this? One's 0.100, the other's 0.300. This has no impact on the coefficients. It's a concentration. This one's the limiting reagent. This one's the excess reagent. It depends on the amounts. If this is 0.05 and this 0.1, this is the limiting reagent. It's the excess reagent. You have to do this. If this were 1, then that's a big difference. If this were 1, then this is a limiting reagent. What you do when you do these problems is you think of the different scenarios that you're going to encounter. How many different variations of this are there? Well, there are a lot. And then you think, well, some of them are going to have the left one bigger, the right one smaller, or whatever else. So you think of different scenarios that you might encounter. We did. I purposely did a few scenarios in the reset. And there aren't that many types of problems that you encounter. And so we reset this, and then we end up with this, and then there's a change. The change now has to go back. Otherwise, these can't stay 0. This is going to be plus 2x, minus 2x, minus x. And so at equilibrium, we're going to have 2x molar, 0.200, minus 2x molar, 0.150, minus x. Is this what you got so far? This one? All right, then we'll just plug it in here. This is going to be 0.200 minus 2x times 0.150 minus x divided by 2x to the 4th here. Now, this favors the product, so what I would do here at this point is just try the simplifying assumption. Yes? Yeah, sorry. That's another common mistake. People will square it here but forget to square it here. Actually, that is a very common mistake, actually. But good you caught it. Then what? If we try the simplifying assumption, this is going to be 0.200 squared, 0.150 over 2 times 2 is 4 times 2 is 8 times 2 is 16. 16x is 4. And then solve for x here. So solving for x, I would get this 0.2 squared divided by 0.15, I mean times 0.15, times 0.15, divided by 1.09 times 10 to the 5. Okay, divided by 16. And then just square root that twice. And with the simplifying assumption, x is equal to 0.007658. I'll just carry some extra digits here. Now what's going to be, okay, what's going to be a bigger change here? 2x versus 2.2 or x versus 0.15? 2x versus 0.2. The way I figure out which one's going to be a bigger percent change is, this is 2x, so I'll double this. If I double this, that would be 2x versus 0.3. I'd have to double this. So 2x versus 0.3 versus 2x versus 0.2. 2x versus 0.2 is a bigger change. And so this is what I'm going to use to calculate my percent change, the bigger one. And so that means the percent change is going to be 2x over 0.2 times 100 percent. And so I'll just take this times 2 divided by 0.2 times 100. And the percent change comes out to 7.65%. Okay, let me tell you what the next mistake was. So the next common mistake on this problem was this. People calculated the percent change based on this. Do you know what the percent change based on this one comes out to? Less than 5%, which is valid. And so they only calculated the percent change here, and they said the simplifying assumption is valid, and then went ahead and used it. But that's wrong. And so this was purposely made this way to see which one you calculated the percent change on. And so we cannot use the simplifying assumption base. We could do it selectively. For example, you could do it on this one, but you can't do it on that one. But the math doesn't become that much easier. And so a simplifying assumption fails. However, it depends on how much time you have. If you're starting to run out of time, then you might write me a little note saying, you know, I'm running out of time, I don't have time. This answer is going to be somewhat close, you know, but it's going to be off. Nobody did that though, but I was seeing if somebody would do that. And so at least you come up with an answer, you know, saying that these are the approximate concentrations we expect at equilibrium, which is better than no answer at all. You know, no answer is not good. And so an answer that's off is better than nothing at all. And the answer that's off, as long as you talk about the...
My calculator is right, but I keep getting 7.6, sometimes it's -4, not -3. And if that's right, then that would bring it down to 5%.
Oh, is it? I might have made an error. If it's 7.6 times 10 to the -4, then
it bring it down.
then it would be okay.
7%.
Okay, so let me double check that calculation. 1.09 times 10 to the 5th. Okay, then what I'm going to do is invert it and then multiply it by 0.2. So invert it times 0.2 times 0.2 squared. Let me just do 0.2 squared times 0.15 equals that, divided by 1.09 times 10 to the 5th equals that,
What did I do?
divided by 16, and then square root it. I still get the same. I don't know. Does anybody else? Do you get the same? I get 10 to the minus 3, not 10 to the minus 4. Actually, I was, you know, I was very careful in selecting these numbers because I wanted it to do just this. I wanted this one to I'm just telling you because this is, I don't want you guys to make the same mistake. And I warn people ahead of time, but even though I warn people, and I warned this class ahead of time, about this just once. And I warned you guys just once, but it's easy to forget. Lots of people forgot, and lots of people did that. It's a common error. All right, so if that fails, then what do we do? What do we do? Successive approximations. And so I'll tell you, a lot of people got this one right, this problem right. They just did the successive approximations. Where would you start with successive approximations? I'd start here, but I'd round this to one digit because it'd be a lot easier. And so my first guess for x would be 0.008, And I think the fewest number of guesses that it took was like 3 or 4 guesses maybe. The most number of guesses it took was, I think, over 20. Okay. And so it depends on how you border it. When we want to border to the same number, and so we go 0.08, but we don't want to start digging too deep. First you do the coarse adjustments, and then you do the fine adjustments. Otherwise, the people who were taking like 20, 25 guesses, some people weren't successful with successive approximations because they were already doing the fine adjustments and they were way too far off. It's like you're scanning the sky to look for Mars, and you're already doing fine adjustments, and you're light years away from Mars. It's going to take you forever to do it. And so we do successive approximations, and then get the x, and then substitute that in there. Is it okay? You guys can finish this one. But that's the basic strategy in solving this one. For 16. Okay. Other questions?
Can I confirm that 11 is C?
11. The equation for K was derived from. Well, now this is tricky because it used to be that chapter 13 was chapter 19. And what came first? K as an empirical equation or K as some theoretical equation derived from thermodynamics? What do you think came first? Well, if you go to chapter 15, the empirical equation came first. And empirical equations are equations based on experimental observations. And so the correct answer for this is the equation for K was derived from experimental observations. K itself is a law, It came from experimental observations because what people did was they just measured the product concentrations and the reactant concentrations and took the ratio. And so that's it. And there's a pattern in that, and that pattern is what we call the law. This is derived. Laws are derived from experimental observations. K is a law, and so you wouldn't say a law is derived from a law in that sense. So D is the correct answer for that. Okay. Other questions?
I just wanted to check, is number 12 worded correct? The answers.
Calcium carbonate. Yeah. Yeah, as long as I have enough moles of calcium carbonate, I don't care, how much there is. 3 moles is a lot of calcium carbonate. It's a lot. The calcium carbonate, it's a lot. Because it's a solid. And calcium oxide, does it matter how much you have? No. As long as you have enough, and I got plenty. 6 moles of calcium oxide should be plenty, and those amounts should be plenty to establish equilibrium. And so the CO2, I just got to figure out, well, Kp, what is Kp? Kp is activity of the products over the activity of reactants. Activity of products is just going to be the partial pressure of CO2. And so Kp is equal to 1.0 at 1200 Kelvin. Therefore, the partial pressure of CO2 is 1 bar. And so the correct answer is B. The numbers are there to throw you off, obviously, because you have to recognize that it's pure solid and you have nothing. I could have put all kinds of bizarre numbers in there, but I didn't have enough room. If I had enough room, I would have put like 2.9634 and then something else, you know. All right, what else? Is that it for the sample test? Any other questions? So this last problem, you had to use every trick, you know, every trick in the book to solve. Number 16.
For number 16, if we solved it out, like, and solve it out in terms of x, can we just plug that into our calculator? We have to solving calculator, or the equation solving calculator?
You can't. You can't. Equation solving calculators aren't allowed. Okay, let me take that back. The rules for this, let me tell you, I personally, I didn't care. At one time, I didn't care if you used a problem-solving calculator, because I know like a TI-82 could carry only 10 digits or so in a calculation. And so you know what I did? I would pick my numbers so your calculator rounded off and got like 100% reaction or 0% reaction. I used to do that in these. But now the department has adopted the policy, and this is a standard policy now. You're only allowed the calculator that you're allowed on standardized tests, like the MCAT or whatever else. You're only allowed that, the SAT calculator. And so any calculator more sophisticated than that, you're not. And so you could you could do third order. But if you tell me you're going to use your programmable calculator, then I'm going to make sure that the problem fails with your programmable calculator. It's true. And a lot of people who relied on their programmable calculator weren't able to solve the problem. You know, and I'll guarantee you I'll make it to fail.
The calculator you suggested, if you have one of those, we're allowed to use that, right?
You're allowed to use that, but it's going to fail for this too, because it's a fourth order. This is a fourth order polynomial. That calculator will solve up to third order polynomials. I used to allow all kinds. Now, I didn't care if you used it or not, but the thing is, you know, eventually this is the way science works. This is just your initial taste. In science, the math gets too horrendous. Everybody has to learn how to use these types of tricks or these types of approximation methods in order to do any calculation in science, because the math is look at the Schrodinger equation. You know, there are a lot of people who've had differential equations. Once you have differential equations, you can solve the Schrodinger equation exactly for one atom, you know, hydrogen or one electron species. Everything else, the math is too horrendous. So how do you solve it? Well, if I buy a more expensive calculator, will that solve it? No, absolutely not. Even with the supercomputer, are you going to solve it exactly? No. And so you're going to run into this problem sooner or later, where you're just going to have to, you know, and it's better sooner than later, that you're just going to have to deal with it, because the technology, you aren't going to be able to solve it. Okay.
Is there a way to like finish that problem?
Yeah, we could finish this problem.
Okay.
But this one doesn't take very long. Let's see how many guesses we can do it in. All right, so 0.08 times 2 is 0.016. So 0.2 minus 0.016 would give me 0.184. So 0.184 squared. Although I wish I had my other calculator. I'm going to do this rather than my phone. Times 0.150 minus 8 would be 142. So times 0.142.
Do you want to borrow my calculator?
Well, I don't know if I'd be any faster because I'm used to my calculator.
Oh, okay.
My calculator is the Casio FX115.
I got that one.
Oh, do you?
That's you.
No, I want you to do it too.
Okay.
2 times 0.016 to the fourth divided by 0.016 to the fourth. Other common errors are, even though this is Chem 1B, there's still problems with how you key in certain numbers. So this is why I'd like you guys to do the calculation too. Divided by 1.09 times 10 to the fifth. Or no. Anyway, I get 7.33 times 10 to the fifth. So 7.33 times 10 to the fifth is too big, so we'll bring it down. And now I don't know if bringing this down will bring it down or vice versa. So we just try it, and I don't want to think too much about it. We'll just try 0.07, and see if that does it. And so if we go 0.07 times 2 is 0.0114, so 200 minus 14 would be 186. So 0.186 squared times 150 minus 14 would be 136 times 0.136 divided by, this would be 0.014 to the fourth divided by 0.014 to the fourth. And I went the wrong way. I got 12.24 times 10 to the fifth. Well, that's okay because I should have gone to 0.009. And I should have known that because it's fourth order on the denominator, third order numerator, maybe. And so let's try 0.09 and see where that brings us. Which would be 0.018. So 200 minus 18 would be 182. 0.182 squared. And then 150 minus 9. Did I screw that up? I screwed this one up because I did 150 minus, not 7, 150 minus. But it's all right. Let's just do this one. 150 minus 9 is going to be 141 times 0.141 divided by 0.018 to the fourth. .44 times 10 to the fifth. So what should I try? This is still pretty big. I was hoping I would be a lot closer than that. And so what would you try next?
So for my point 007, I got 4.24 times 10 to the fourth.
Oh.
So I make it a little bit larger than that.
12.24 times 10 to the fourth you got?
Yeah.
Okay. 12.24 times 10 to the fourth, we want to make it 10 to the fifth. So if I make this one bigger, I got to make this one smaller.
Yeah.
So I went the right way, unfortunately.
I make it a little bit bigger than .07.
Yeah. Okay, a little bit bigger than .007 would make this one a little. Actually, do we want to go a little smaller? We want 1.09.
Oh, yeah.
You got 1.22? Let's go a little bit smaller because it looks like we're going from 1 to 7 here. So if we're going to 1 to 7, we want it just a hair small. Let's, but you know what? Let's just try .06 because just to border. That would be 200 minus 12 would be 188. 0.188 squared. This would be 144. 144. Divided by 1012 to the fourth. You made. What did you get? I get 2.45 times 10 to the fifth, so
Same.
same. So you were right. We should have gone smaller. I mean, bigger, a little bit bigger than this, perhaps. Although it's hard because, you know, this is one of these kind of functions that does this kind of stuff, so gotta figure it out.
Entire order on the bottom.
Yeah, so which way should we go? To .0075? You wanna try that?
How long did it take you to come up with the problem?
Huh?
How long did it take you to come up with the problem?
I had to play around with it a little bit, that's all. It can, takes some time to come up with the problems. But since I don't do a calculator check, I'm going to come up with a very special problem for you guys.
$9.6.
9.6 times 10 to the fourth. 0.96 times 10 to the 5. Oh, you're very close. So this is 70, 80. So we want to go closer to 70. So this is 1, 2, that's 1. We want 1, 1. So halfway between these two should be it. What did you do? 73 or 72? 72? All right, try 72. This is a good practice. To punch it into your calculator. I mean, because you're just training yourself for what you might have to do on the test. You know? 1.14 times 10 to the fifth. Well, that's good. But I'm still not good enough. And so let's see here. So it's still between 75 and 72 now. So it looks like Should we try 0.073? So 0.0073. 0.073 times 2. I'm going to stop doing it in my head. Minus 0.2. Does that square this? Times 0.15 minus 0.73. Equals divided by 0.073 times 2 is 146. Or 1.079. Wow. 1.079 times 10 to the fifth. This is almost, this is 1.08. So close. But I want 1.09. I mean, that's to 3 bigs. We've got to get it to 1.09. And so what do we need to do? Go a little bit higher or a little bit lower? A little bit higher. So we're at 108. This is 114. So we're going from 8 to 14. 8 to 14, 6 units. So we'll divide this into 5. And so I would go 732. What do you think? Yeah, 0.00732 or 731, something like that. We'll try 732. We'll get more significant. What's that?
Shouldn't you go the other way? So that.
Oh yeah, you're right. We want to go 2 below this. 728 is what we want. Because it's between these two. Excuse me. 728. All right, so let's try that. 0.00728 times 2 minus 0.2 square that times parentheses point. 728 times 2. 1, 4, 5, 6. 1.0. 1, 4, 5, 6 squared. Doesn't do parentheses very well.
1.0.
Well, we need 1.09 what?
2.
Okay, then it's okay. As long as it rounds to 1.09. If it was like 1.095 or higher, I'd keep trying.
And if it were 5, would you do?
If it were 5, I would, I'd adjust a little bit. We want this to round to 1.09 like that. That's all. And so it does. And so then we'd be done here. So x is equal to this. So once I have my x value, then I'll just plug it in here. This will be the x value for ice table number 2, the reset ice table. The x value for ice table number 1 will be something totally different, but we'd end up with the same equilibrium concentrations. And so 0.00728 times 2, 0.01456, is that it? All right, so these would be the equilibrium concentrations here. What are the equilibrium concentrations? That's what the question is asking for. And then we would want to double check this just to make sure we didn't make some simple mistake here, or I didn't make some simple mistake adding and subtracting these. And so it's going to be this concentration squared times this concentration. So let's go ahead and do that. 18544 divided by this concentration to the fourth. And K comes out to 1092 times 10 to the fifth. And so we're good. So I'm done. Well, how many guesses was that here? 1, 2, 3, 4, 5, 6, 7, 8. 8 guesses. So not bad. Probably not the best. The most efficient, but not bad.
So say you're on a test and you did a simplifying assumption and you got 7.65%, and you didn't have enough time to go through. Could you like say, oh, this is?
Yeah, you know, if I were on a test
Yeah.
and I'm running out of time, I would go ahead and use that.
Okay.
I'd say, you know, because look at it, it's 728, 7658 is not terrible. You know, it's much better having this number than no number at all. And so what you could do is you could say, well, I'm running out of time, so I don't have enough time to do this. I'm just going to use this and get these concentrations. Now, if we use that, what kind of K value would we have gotten? And so I would have just went ahead and at least come up with some ballpark. Oops, I shouldn't erase. I don't need to erase it. Rather than getting 0.0156, 1456 molar here, with the successive approximations, we would have gotten 0.014, 7658. We would have gotten 0.015316 molar here, 0.015316 molar here, and then 184.684. These would have been the concentrations we'd have gotten. I mean, at 7%, what's the difference? Some people might say, what's the difference? You know, 7.7% versus 5%. Does it really make that? You know, the error is already so big. Is that really going to be that much more significant? You know, in other words, the 5% cutoff is totally arbitrary, and so some people might argue that 5%. Change is already so huge that if the difference between 5% and 7%, you're still going to have significant error in that calculation. The cutoff should be a lot lower. And so, you could argue that it's close. 7.8% versus 5%, it's close in relative terms. Now, if we did the double check here, let's compare, what kind of percent error we would have gotten the K value here if we went ahead and used this. And so it would have been 0.184684. Square times 0.1423 divided by 0.015316. And so if we did our double check, it would have came out to 8.82 times 10 to the fifth. 8.82 times, oh, not times 10 to the fifth, times 10 to the fourth. 8.82, which gives us 0.882 times 10 to the fifth. And so rather than having a 1.09, we got 0.88. Yeah, it's like a 20% error or something. Maybe it's okay. But it's better than no answer at all. You know, a ballpark answer is way better than nothing. So you would have gotten a lot more points if you just went ahead and finished versus giving up and saying it's all right, is that it for the questions on this? Well, you know, we finished chapter 16 last week, right? And so officially the chapter 16 test is supposed to be this week, but we're having the chapter 17 test this week. And so think about the chapter 15 test, yeah. Think about the chapter 16 test, you know, next week. What do you guys think? Next week on Wednesday or something? Or possibly Thursday. Thursday they're having the earthquake drill, so I'm not sure. 17 is, yeah, we're going to do a 17 calculation today, right now. And I'll ask you if you want to combine it. 16, they keep it simple because it's just acid plus water or base plus water. 17, we have lots of variations. And in fact, we're going to take a look at the variation right now. It gets a lot more complicated because there's so many equilibria that we can potentially deal with, and a lot of them we don't need to because they're redundant. But where did we leave off last time? We calculated the pH of the water with 1 drop of acid. Did we do it to the buffer too? Did we calculate the pH of the buffer? Or did we figure out a pH 7 buffer yet?
Yeah.
We figured out a pH 7 buffer? When you want to make a buffer, what you do is you look for a acid with a pKa close to the desired pH. Which one did we use? Dihydrogen phosphate and monohydrogen phosphate?
Yeah.
And we got a ratio? Okay. And so what we could do is we could mix like sodium dihydrogen phosphate and sodium monohydrogen phosphate. In the right ratio. If we mix these in the right ratio, then that will get us the right buffer. Actually, I want to mix 1 molar monohydrogen phosphate. How much dihydrogen phosphate will I need if I use 1 molar monohydrogen phosphate?
We got
0.063. 63 what? 6308? 6309? 6309. What I'm going to do is I'm going to invert that so I can get just 1.58. If I do this, I'll get the same ratio. If I go 1 molar monohydrogen phosphate and 1.58, 5 molar dihydrogen phosphate, this should give me a pH 7.00 buffer. Now, I just have to mix it up in this ratio, so I can pick whatever concentrations I want as long as it stays in this ratio. One thing I could do, though, is I could get the same pH by using less. And so this we'll say is our higher capacity buffer. Did we do a calculation yet with this? No, I don't think so. And then we could have a lower capacity. A lower capacity buffer is just going to either be a lower volume. For example, if I only have 10 milliliters, you know, versus 1,000 milliliters, 10 milliliters is not much buffer. And so that would be lower capacity than 1,000 milliliters. But another thing that could give us lower capacity is just lower concentrations. So I'm going to cut the concentrations by 1,000-fold. So we're going to go 0.001 molar monohydrogen phosphate and 0.001585 molar dihydrogen phosphate. Now, the ratio didn't change. If the ratio didn't change, the pH would still be the same, and the pH is going to be 7.00. The difference is in the capacity, you know, and let's keep the volumes the same. This is going to have a much lower capacity. And so they're going, what I mean by capacity is capacity to neutralize added acids or added bases. So one thing we'll subject this buffer to is 1 drop of 6 molar HCl. And then we'll do the same thing here. We'll take the lower capacity buffer and add 1 drop of 6 molar HCl, and then see what happens. And so this will be the first calculation, calculation A, and then we'll take the lower capacity buffer and do the same calculation, calculation B. Now, Chapter 17 problems, the strategy is different between Chapter 16 and Chapter 17. In Chapter 16, it's just acid and water, so we don't have to do step I. Step I, you know, it's already acid in water, or it's already base in water, so step I is not necessary. For Chapter 17, we have to do step I, and what step I is do you know what step I is? Step I is solution dilution. And so in Chapter 17, we normally start off with solution dilution. And so let's look at A first. When we add 1 drop to 10 milliliters, then the total volume goes to 10.05 milliliters because a drop is about 0.05 milliliters. And so the volumes increase because we're mixing together 2 solutions. If the volume increases, then the concentrations have changed. Now, I'm going to have the HCl concentration. This is called the HCl initial. It's not the original HCl concentration. The original HCl concentration is 6 molar. But when I mix the solutions, well, the concentration has changed. That 6 molar is no longer valid. And so this is the initial concentration before reaction, but after solution dilution. And so the, did I talk about the dilution factor already? You know about dilution factors? Solution dilution, we're looking at diluting. So the molarity of the dilute solution is equal to the volume of the concentrated solution divided by the volume of the dilute solution times the molarity of the concentrated solution. This is the M1 V1 is equal to M2 V2 equation. This ratio, this fraction here is called the dilution factor. And so the dilution factor is 0.05 of the concentrated 6 molar HCl divided by 10.05 of the total dilute. So it's a 0.05 to 10.05 dilution of 6.0 molar. This is going to give me 0.02. Let's figure it out. Actually, this is the same calculation we did earlier. 0.05 divided by 10.05 times 6, 0.0298. 5 molar HCl. And so this is initial concentration of the HCl in the mixture, the reaction mixture, before anything reacts. And then we have HPO4 2 minus. The HPO4 2 minus is going to have a different dilution factor because we're starting off with 10 milliliters of that. And so we're going to start off with 10 milliliters, 10.00 milliliters, and then we're diluting to 10.05. So it's a 10 to 10.05 dilution. A 10 to 10.05 dilution is like negligible. You might say nothing's changed. But what we're doing in Chem 1B is we're just looking for these changes, which can be big changes or very small changes. We don't want to do this Chem 1A style where we're just going to say, oh, the change is negligible here. Not bother. So we're going to actually look at the change here. And so this is a 1 molar. I'm going to carry extra digits. So 10 over 10.05 gives us what? Gives us 0.9950 molar. Actually, I'm going to carry 5 decimals. The reason I'm going to carry 5 decimals. for the next calculation. So I'll just be consistent with this calculation. This is gonna be H2PO4 minus. Again, this is gonna be a 10 to 1005 dilution. The molarity is 1.5 or 1.585 molar. 1.585 molar. And this is going to give me 1.577. Sometimes, you know, these dilutions are so small, we got to carry extra digits, otherwise we lose the dilution. So I'll go 1.57711 molar. All right, this is what we call, or what I call, step I. Step I is solution dilution. Now, there are different approaches you can do. I like to do solution dilution. Some people like to just calculate how many moles. I don't necessarily do that because I want to see, you know, does that concentration make sense, or, you know, are these concentrations reasonable? You know, how high are the concentrations going? Because we need an idea about the concentration. Because, you know, in the back of our mind, we've got to think, if the concentration gets very high, we're going to deviate considerably from ideal behavior. And that's going to screw up the calculations anyway. And so it gives you some kind of idea about these types of things. So I like to do concentrations. These concentrations are fairly low. All right, then we go to step 1. In chapter 17, all the problems are the same. You know, step 1 is always the same. Chapter 16, it's all the same too. It's acid plus water or base plus water. In other words, water can act either as an acid or base. And so it's an acid plus base. In chapter 17, we just modify that a little bit. Rather than acid plus water, we say acid plus base. In other words, in chapter 17, we just say the strongest acid plus the strongest base. That's our ice table. And so what's the strongest acid present in this is the reaction mixture. And so all these are the initial reaction mixture. What's going to happen? Well, it's going to react. What's going to react? The strongest acid will react with the strongest base. So what's the strongest acid present in the reaction mixture? HCl. The strongest base? HPO4 2-. This is the difference between chapter 16 and chapter 17. In chapter 17, we're going to have other bases other than water and other acids other than water. And so here, this is going to form what? Cl minus plus H2PO4 minus. What's K for this reaction? Equal to? Anybody know what K for this reaction is? It's not, I wouldn't say really high. I wouldn't say large, I wouldn't say very large, I would say very, very large. This one is very, very large. Why? It's because of my relative scale that I came up with or showed you earlier. It's the relative scale. There are 3 phases of large. Very large, very, very large, and very, very, very large. Well, this is a very, very large. But you know, it doesn't matter because it's going to react to. You know, if you put very large here, I wouldn't deduct you any points. You know, because it's going to end up doing the same thing. The only reason I want very, very is so you also know the relative scale. So HCl here, we'll just plug it in. It's going to be 0.02985. And so what happens is the base part of the buffer, this is the base part of the buffer, is going to attack or neutralize the acid. And so the base part is going to be 0.99502. I'm just going to carry extra digits and I'm going to round it at the end. And so we have 0 chloride and 0 H2PO4 minus. Now with a K value like that, it tells you the reaction is complete. So we look for the limiting reagent. Which of these two is the limiting reagent? HCl or HPO4 minus? HCl. And so what happens is the buffer completely neutralizes all the HCl. We should have no HCl left. And that's what the buffer's job, to do that. So this is minus this. It's going to be minus 0.02985 molar. But in the process, we lost a little bit of the base component of the buffer. So we start off with 0.99502, and we lose 0.02985. Wow. Let me do that one more time. 0.99502 minus 0.02985. We have 0.96517 molar. And this will be 0.02985 molar. This will be 0.02985 molar. Okay, then for step 2, we repeat. We take the strongest acid plus the strongest base present. The strongest acid present is going to be, well, we no longer have HCl, but we do have. You know what? I made a mistake here. Shoot. You see my mistake? You see my mistake? My mistake was this.
Oh.
We don't start off with 0. Yeah. That was my mistake. But we're out of time, so I'm trying to rush through it. Tomorrow we're going to meet in the computer lab. We're going to do